uh, about. I hope that you can see the whiteboard. Two-dimensional steady
Yes,
state.
sir.
Okay, steady state heat conduction, and we did two methods in that. One was nodal network, which is a type of FDM, which is finite difference method, and then the second one was energy balance method, which is FVM, which is finite volume method. So now we are going to look at the transient heat conduction problem. So for that we would discuss the. So now we are going to discuss one topic from chapter number 5. So this was basically chapter number 4. So now we are going to discuss one topic from chapter number 5. So that is lumped capacitance method. So before we start discussing this method, can you tell me or tell the class that any example of any transient heat conduction, any practical problem where you can see any conduction happening in transient cases? If we talk about any example from the daily life rather than engineering problem, we would discuss that later. But let's discuss anything from practical problem. Any. Have you ever done any barbecue?
जी sir.
जी, so if you know that we kind of use coals for those barbecues, so first of all we uh, kind of use that burning coals to roast meat, or maybe we. So in that case, if we start from time t is equal to 0, so at time t is equal to 0, that is the time when we put that meat on the barbecue, and then after some time, maybe 10 minutes, that meat is prepared to be ready to serve. So that is one example that BBQ I have given you. And then another example, that whenever you want to make tea at home, so if you put fire under a uh, kettle, then what happens that first of all that fire heats up the bottom surface of the kettle, and then from there the heat transfer to the top surface, and then because after having some after some time, that kettle surface, bottom surface, becomes quite heated. So it means that in that problem, the this problem is temperature is function of time. So it means that we are talking about transient heat conduction. Okay, so these were the two examples which I gave you from the our daily life. Now, any example from engineering perspective you can think of? Have you studied a course named manufacturing processes?
इसी semester कर रहे हैं sir.
जी,
नहीं अभी तक।
अभी पढ़ रहे हैं आप?
यस सर।
जी
ओके
sir
जी,
इस semester में.
उसके अंदर आपने कोई हीट ट्रीटमेंट प्रोसेसेस पढ़े हैं? या डाई कास्टिंग, या कोई ऐसी
कास्टिंग पार्टी है सर।
जी? अच्छा जी, कास्टिंग में क्या होता है कि आमतौर पे वी काइंड ऑफ यूज अ फर्नेस टू have that metal in a molten state, and then we kind of cool it down by using either in an open air, that is the process of annealing, or we put it in some liquid like water, that process is called annealing. So that process, if we have got here, just a minute. So if we, okay, just a minute, let me hide this. So uh, if we have got a container here, which is full of water, and then at time t less than or equal to 0, that metal which we heated in a furnace at that temperature is T is equal to Ti. Then if we put it at time T is equal to 0, if we put that in this kind of water, so this process is called quenching. So here the water temperature here T infinity is always less than Ti. So that's why the heat would be transferred from this heated metal to this surrounding fluid. So it means that here the temperature is function of time. Here this numerator here capital T is temperature, and in the denominator the small t is time. So here we can say that partial t by partial small t, that would be less than 0. Less than 0, it means that temperature would decrease, temperature of this metal would decrease with time. So it means that this object is losing heat. So that's why the temperature is being decreased. So now in the lumped capacitance method, which we are going to discuss, we say that what is the English meaning of lump? Anyone in the class? What is a lump? What is English meaning? What is meanings of lump? We say that anything which can be considered as one, as a unit. So we say lump sum. We have got this thing. So as one unit. So in here in HMT, when we say lump, it means that we are saying that the temperature of that object is uniform. When we say uniform word, what does it mean? It means that, uniform means that there is no gradient of temperature with respect to x, with respect to y, and with respect to z. All these gradients are equal to 0. So it means that whatever the temperature of this object at the boundary, whatever the temperature at the boundary, the same temperature would be at the center of that object. So it means, so in terms of heat transfer conduction, when would that occur? That case, that would occur when K is very large value, or maybe we can say it approaches to infinity. So it means that when the thermal conductivity of the this object is very high as compared to the convection resistance which is being offered by the surrounding fluid, then we can say that uh, this object is totally at the same temperature which is at the boundary. So it means that when we say that we are considering or assuming the lumped capacitance method, then we say that the temperature within that object is uniform, which means that there is no gradient of temperature with respect to space. So it means that we are talking about only temperature variation with time, which is partial T by partial capital T by partial small t, because here it is a variation of temperature with time, right? So now, sorry, if we kind of apply the energy balance on this object. So now I think one thing is clear, that in lumped capacitance method we say that thermal conductivity of the object is very high, which means that the thermal conduction resistance is very low, and the thermal convection resistance uh, is very high. right? So now if we apply the energy balance over this uh, metal which is being cooled down, so if we write the equation here, energy balance equation, that would be E dot in plus E dot st minus E dot out equal to 0. Oh, sorry, not 0, because 0 would only be in case of steady state problem. So that would be equal to E dot st. So here E dot in is the rate of heat transfer into uh, this metal object, and then E dot st is the rate of energy generation, which would be equal to 0 unless it is a radioactive material. Then minus E dot out is the energy going out of this object. So, and then E dot st is the rate of change of stored energy. So if for this case, where the quenching process is, quenching is the rapid cooling of this object by putting it into some liquid, which is maybe water. So if we kind of simplify this equation, so E dot in would be equal to 0 for this case, because this object is losing energy, so nothing is coming in this case. So E dot in would be equal to 0. And because this is a simple metal, not a radioactive metal, so E dot st would be equal to 0. Now we are left with minus E dot st minus E dot out is equal to E dot st. So now if we further simplify, further write, want to write, what would be E dot out? How can we write E dot out? That is basically the heat transfer due to convection. So we can write minus h into as. As is the surface area of this object into T, which is function of temperature. So here I am showing this, but we can ignore this. We know that this is function of, and just a minute. So we can say that this is function of temperature minus T infinity. Okay, what is E dot st? That is m into C. C is the specific heat capacity. That would be Cp in the case, but because for the solid it would be Cp is equal to Cv is equal to C, so we write it C. So this is specific heat, and then partial T by partial time. So variation of rate of change of time temperature with respect to time. Right. So now if we define another variable, because here what is the main interesting thing for the convection, that is T minus T infinity. So we introduce a variable theta, which is equal to T minus T infinity. So if we take derivative of theta with respect to time on, then we can write partial theta upon partial T would be equal to partial T by partial T minus partial T infinity by partial T. Now because we know that T infinity is the temperature of the sink, which is the surrounding fluid, so that remains largely in, unchanged with time. So we say that this second term is equal to 0, because this is the rate of change of sink temperature where the heat is being lost. So because we say that the container is quite large, so whenever this object loses heat, the T infinity doesn't change very much with time. So we say that this is equal to 0. So now partial theta by partial time is equal to partial T by partial infinity. We can put it here. So this equation would this equation 1 can be uh, written in terms of theta, which would be equal to minus HAS theta, because theta is equal to T minus T infinity. So we just put it this here, and then on the right hand side m into C into partial theta upon partial t, that is from here, right? So now, oh sorry, now if we write what is m here, m is basically mass, so we can write mass is equal to m is equal to rho v. Rho is density and v is the volume, so rho v. So we can write theta is equal to rho v c divided by HAS. Here it would be minus this one partial theta by partial, right? So sorry, and now we can do the method of separation of variables. So what we do here, that the variable involving theta would come on the one side, and the variable involving t would come on the other side. So we can write partial theta on partial t. Now partial can be written in terms of d, because this is temperature is only dependent upon time here. So d theta upon dt would be equal to minus, it would be equal to minus HAS rho Vc into dt. And if we put the limits for the integration here, sorry, here it should be not dt, where dt would come on the right hand side, so here it would be theta. So and let me make it more clear, this is d theta. So the limits would be from time t is equal to 0, so to some time t here, right? And for that we would have the limits here, theta I to theta, where theta I is basically T of I minus T of infinity, where T of I is the initial temperature of this object when it is put into that water, right? And theta is some at other time t minus T of temperature as a function of time. So if we do the integration, it is quite simple. So we know that d theta by theta, if we integrate it, that is equal to log of theta, theta, theta I, and then here it would be minus HAS rho Vc into time. Time limit would be equal to uh, t and 0. So we can write it further by, like this: log of theta upon theta I. I hope that you understand that when we take the log of theta minus log of theta I, we can write it in ratio form. That is the property of natural log minus HAS rho Vc into time. Time is because when we put the limit, the above limit would be time and the lower limit would be 0. So we are left with this equation. So now we can see that we have got a relation for this. So now if we want to calculate this, uh, uh, so now if we want to calculate theta from here, what do we need to do? Anyone?
एंटी लॉग ले लेंगे सर.
एंटी लॉग या फिर एक्सपोनेंट फंक्शन ले लेंगे. थैंक यू वेरी मच हारिस. सो when we do that anti log which is exponent function, so it would become theta upon, just a minute, theta upon theta I, which is basically equal to t minus t infinity divided by t of I minus t of infinity is equal to e raised to power t upon tau. Now this whole bit I have, let me clarify a little bit. This whole bit here, it should be also minus. So this whole bit I have taken it equal to tau. Okay, and tau is the thermal time constant. And because why I call it constant, because H is a property which is related with the fluid. AS is the surface area of that, so it means these are the properties which we know. So that's why I am calling it tau is. If I write it here, tau is thermal time constant. Thermal time constant, and its value is equal to rho Vc upon HAS. Right. So this is the definition. So basically, we have written it in a very concise form. So now there are two things we can do. That time would be this t would be equal to rho Vc upon Hs into log of theta upon theta. That is the time which is required for this cooling to happen. And the second thing, if we want to calculate that after certain time, how much this fluid has been cooled, then we can write it theta would be equal to theta I e to power minus t upon tau. And then if we write it a little bit in temperature, then we can write T minus T infinity is equal to T I minus T infinity into e to power minus T upon tau. Right. So if we want to calculate temperature of this object after some time t, then t would be equal to T infinity. This is of course function of time, T infinity plus Ti minus T infinity e to power minus T upon tau. Right. And this thing, and the second relation which I told you, that if we want to get time from here, then what we need to do, that if I go back a little bit, if want to calculate time from here, then I take log of both sides, then e exponent would be cancelled out, and then if we write time from here, from this equation, time would be equal to, from this equation, I'm talking about from this equation, time would be equal to, time would be equal to, I can write it rho Vc upon HAS into log of theta I upon theta. Now you must note that we have got minus here. So that minus, when it would go to the left hand side, so this would make it log of theta I upon theta, and then this bit which is 1 upon tau, when it would go on to the right hand side, that would be equal to tau. So tau is equal to rho Vc upon HF. So I have written these two formulas. So now let me encircle these two equations, because these are the two formulas which we need to calculate. What is this time? That is the time required to get an object which was at theta I to reach some temperature which is T, which is here in the denominator of this natural log function, right? And the second formula which we may need for the calculation, that is the, if we are given that if an object is being put into a fluid or into a medium, then after some time t, what is its temperature, then we need to use this one. Okay. So this gives you the value of temperature after some time t, and this gives you the time required for an object to reach some specific temperature, right? So these are the two formulas which we may need in the uh, in the in the numericals. Okay. So sorry. So now, what is the? Let me kind of go you take you at the beginning of this lecture. Here, if you know, if you remember that lumped capacitance method was the name of this method. Now, lumped we discussed in the beginning that what does it mean? This lumped, that T is only T is uniform in inside this object. So it means that partial T by partial X, partial T by partial Y, and partial T by partial Z is equal to 0. So temperature is only function of time. So that explains this lumped thing. But what is capacitance here? So now we need to define the thermal capacitance because that is being used in this. So we need to identify that. So let me uh, go back at the final equation. Now, if I write this thermal time constant tau again, tau is equal to, if I rho Vc upon Hs, rho Vc upon Hs. So I can write it a little bit in rearranged form. I can write it 1 upon Hs, and this is rho Vc. So this is sorry. This first term, what is this? This is thermal resistance of the surrounding fluid. So we call it RT. And what is this? This is the ability of that material to store thermal energy, because rho into V is mass and C is the specific heat capacity. So that is our CT, which is, this is called thermal capacitance. This is thermal convection resistance of the surrounding fluid. We know that. Thermal resistance, convection. Right. So that is that gives this method the name of lumped capacitance method. So now this tau defines that how the temperature would vary. If this tau value is quite low, then the temperature would change rapidly. But if tau is high, then this temperature would vary a little bit less at the uh, lower speed. So let me show you that graph. Here it is, if I kind of make it a little bit more, maybe 400 would be good. I think now we can see it more clearly, right? So now if you look at this graph, now we have got on the x-axis we have got time that and on the y-axis we have got the temperature ratio theta upon theta I. So at the beginning, when time is equal to 0, then theta is equal to theta I. So it means that all the curve would start at 1, because theta would be equal to theta I at time t is equal to 0. So this would be equal to, here in the numerator we would have, instead of t we would have ti. So that would be equal to 1. So theta would be equal to theta I. So you see that all the curves start from 1. Now as we change the tau, if we have got tau value less, then the change in temperature is quite rapid. Rapid it means that this uh, theta value decreases quite sharply if we have larger value, smaller value of t. But as we increase tau, then this, because when we are increasing tau, we are increasing the thermal capacitance of that object. This is the rho we see, right? So increasing the T means that when the thermal capacitance is more, then it means that it can store more energy and it can have more less resistance to the convection. So it means that when the thermal capacitance is more, then it will lose energy slowly. So so you can see that as we are increasing tau, that this slope becomes less and less, right? In the beginning, it is for the lowest value of tau, it is very large, it is changing very rapidly. But as we increase it, because of the increase in thermal capacitance, so the change in temperature becomes more gradual and gradual, right? So if the thermal capacitance is high, then the object would cool down very slowly. But if the thermal capacitance is low, it would give energy more rapidly to the surrounding fluid. So I hope that this point is clear to all. Okay. So now let us go back to the slides, whiteboard. So now we have defined up till the equation. We have just studied the physical significance of this thermal time constant, about the thermal capacitance and how it makes the transient process more rapid or gradual. So now if we want to know that what is the total amount of heat transfer which has happened during our transient process, so that can be calculated by integration. Oh, sorry. So for that, if we here we write total amount of heat transfer, that would be equal to Q is equal to, because in this the heat is being transferred by convection, so we can write HAS into, that would be equal to HAS into anyone, that would be equal to theta, which is basically T minus T infinity into dt, which is over a time period. So time period would be from 0 to some time t. Now what is theta? Theta can be written in terms of theta I from this relation. Let me show you the relation. This one. Theta is equal to theta I exponent minus t upon tau. Come on. So all we need to do is put that value here. HAS theta I e to power minus t upon tau into dt. So because theta is independent of time, so we can write Q is equal to HAS theta I. Now if we take the integral here, so we know that when we take the integral, it would be something minus 1 upon tau into e to power minus t limits 0 to t, right? So if we do the simplification, then it would be tau into HAS theta I. Here, of course, we have got minus, and in this we would have e to the power minus t. And t, sorry, here it should also be tau. T upon tau minus 0. Minus 1, sorry, because exponent, because when we say time t is equal to 0, then exponent 0 would be equal to 1. Right? So we have got minus in the beginning, so we can write it q is equal to, now what is the value of tau? We can just put that value of tau, which is equal to, what is the value of tau here? If we go back, tau is equal
RC,
to बिल्कुल RC which is equal to rho VC upon HA. Uh, so if we put the value of uh, that, so tau would be equal to rho VC upon HAS. This is tau. Then we have got HAS theta I, and then when we take this minus into this, then this term becomes 1 minus exponent minus t upon tau. So now this thing will be cancelled out. So we are left with rho VC into theta I. So if I cancel this thing out, so we have got rho VC into theta I, which is the initial temperature. What is theta I here? Ti minus T infinity. Ti is the initial temperature of that object. T infinity is the fluid temperature in which we have immersed that object, and here we have got 1 minus T upon tau. So this is the relation for total. Here this Q is the, I should represent it with capital Q, which is total amount of heat transfer occurred in the transient problem. And its unit would be equal to kilojoules. Not, because we are multiplying the convection heat transfer with, if you go back to the original equation from where we start the integration, we have multiplied the convection heat transfer rate with the time. So when we multiply something with time, and it is again it is kilojoule per second, so second would be cancelled out with this time, so we would have the unit of this Q. So it should be capital Q, not maybe, because that would be confusing for you all, so I put it equal to capital Q. Right, so I hope that this point is also clear. So now there is one thing left, which is that is the Fourier number. That is a dimensionless time. So how can we have that from from this thermal time constant? So that is, if we here in this equation, if where we have written this log of theta upon theta is equal to minus HAS rho VC into time. We have written this. So if you can remember, that is HAS into time into rho VC. So okay, let's just postpone this discussion. Before that, it is important that we need to know that because this method is applicable when we have got the lumped assumption applicable. So now we would talk about the validity of this method. Sorry, validity of lumped Pestos method. So let's consider for the time being that heat is being transferred from if we have got a rectangular object which is placed in that some fluid for that cooling purpose. So let's draw that rectangular object here. So here we have got temperature T1, here we have got temperature T2, here we have got temperature T infinity K. Here T1 is greater than T2, which is greater than T infinity. So it means that the conduction heat transfer would start from left hand and it would go up till right hand by conduction and then it would go out by convection. So if we apply energy balance here at this wall, surface energy balance, so we can write that Q of conduction is equal to Q of convection, right? So in that case, what would be the Q of conduction? That is basically, if we apply the Fourier law, we can write K into Ka into T1 minus T2 divided by capital L, which is the thickness of this. This is capital L into Q convection, that is equal to HA into T2 minus T infinity. So this is the concept from surface energy balance from chapter number 1. So here if we uh, write the ratio of T1 minus T2 divided by T2 minus T infinity, that would be equal to L upon Ka, L upon Ka divided by 1 upon HA. So we have written this HA in the denominator in this form. So it is equal to the same thing. So if you recognize these two things from your chapter number 3 knowledge, that are basically, this is R of conduction for the plane wall, and then this is R of convection. So now if we simplify this area would be cancelled out, and this is equal to HL upon K. So this quantity HL upon K, that is called, this is a, by the way, this is a dimensionless property. How can we know that? Because units of H is watt per meter square Kelvin, and length is meter. And what is the unit of K? That is watt per meter Kelvin. So here meter would this would be cancelled, and then watt per meter Kelvin. So it is a dimensionless number which is called Biot number, which is uh, we represent it with Bi, which is Biot number. So in order to be this uh, uh, lumped questions method to be applicable to a particular transient problem, as we discussed in the beginning, that the thermal conductivity of that object should be very high. So it means that this R conduction should be very low, right? So when R conduction is very low, so it means that Biot number should be quite less than 1 if we want to have the results of our calculation quite accurate. So it means that if Biot number is very less, which means basically that the conduction resistance is low. So conduction resistance low means that this K value is quite high, which is basically very high than 1, or maybe we can say K goes to infinity, which means that it is very high. So in that case, we would say that Biot number, this lumped capacitance method would be applicable. But the question is, as an engineer, we are more concerned about some numerical values. That Biot number very less than 1, what does it mean? That actually at what number of this ratio HL upon K, we would say that okay, we can apply a lumped capacitance method or not. Then sorry for that. So for this, we say for the simplicity, for our peace of mind, we say that if Biot number is less than 0.1, then we can apply the apply the apply the this lumped questions method. So, but what if that Biot number is greater than zero point 0.1, then it means that lumped questions method cannot be applied. Then we either need to use some more complex situation where there is partial t by partial x is also not equal to 0, but it is some significant value. So it means then we either need to use ANSYS software, some commercial software, or we can do some more complex mathematical solutions. So that is one type of solution which is special variation with the time change, that is given in your book as a section. But because I have already given you a project, so you don't need to go through that. We would limit ourselves, only restrict ourselves to only this lumped questions method. So if there is a transient problem in which there is a special gradient, this space gradient is, of temperature is there as well, then we either need to use some complex analysis, or we use that commercial software and sit, right? So because we have been also given that project, so you can explore different options for that. So Biot number should be quite less than 1. Okay, so here this capital L is the thickness of this material. But usually we have got a very, when we talk about die casting, then we have got quite not a rectangular object, but maybe a random volume, like anything like maybe like this, some part which has been die casted. So for that, this characteristic length, this thickness is very hard to define. So for that, there is a concept of LC, which is characteristic length. Characteristic length. If you remember from your 1D analysis of the fin, there we also defined LC, but there it was meant for corrected length, right? Not the characteristic length, but there it was corrected length that we say that we use insulated tip in boundary condition and then we have to correct the length, right? But here it means that the characteristic length, and that can be easily calculated if we know the volume of this object divided by the surface area of this object, which is A. A is the surface area and then volume is this total volume. So if we know the volume and the area, then we can calculate the characteristic length, right? Now there is, I hope that this point is clear to all, that why we need this characteristic length, because if we have got a random object in which it is hard to define thickness of that object, so then we can define a characteristic length or characteristic thickness for that, which is volume divided by area. Okay, so now there is, because we have talked about Biot number, which is the
सर
dimension. Yes,
ये लेंथ जो है ये बेसिकली थिकनेस ही है ज्योमेट्री की.
बेसिकली ये थिकनेस ही है, क्योंकि थिकनेस कह लें कि करेक्टरिस्टिक लेंथ है जिसके क्रॉस हीट कंडक्शन होनी है. देखे ना, अगर मैं आपको थोड़ा सा ऊपर ले जाऊं, सॉरी, इज इट शारिस?
जी सर मैं ही हूँ.
जी शादिद, यहाँ पे अगर आप देखें तो यहाँ पे कंडक्शन के थ्रू, क्योंकि हम वन डायमेंशनल हीट ले रहे हैं ना यहाँ पे हीट ट्रांसफर, तो उसके लिए थिकनेस ये है. लेकिन अगर ये 3D ऑब्जेक्ट हो तो उसमें क्या होगा कि वो उसमें एक्स में भी हीट ट्रांसफर हो रही होगी, वाई में भी और जेड में भी, ऐसे ही होगा ना. सेंटर पे सबसे
जी सर.
ज़्यादा टेम्परेचर. तो इसमें बेसिकली ये आपको बताता है कि ये जो करेक्टरिस्टिक लेंथ है, it tells you that from the center, if what is the average distance to the boundary, यानी कि हीट को कंडक्शन के लिए कितनी डिस्टेंस चाहिए, ये उस चीज के बारे में बताता है. यानी कि आप इसको कह सकते हैं कि इफेक्टिव डायमीटर एक तरह से इसका, ठीक है, जैसे हाइड्रोलिक
जी
डायमीटर
सर.
आप, ठीक है. जी दोबारा बताइए शारिस.
तीनों डायरेक्शंस के लिए ये एक एवरेज वैल्यू है.
हाँ जी, ये क्योंकि ये जो हमारा ट्रांजिएंट प्रॉब्लम होता है ये आमतौर पे 3 डिमेंशनल केस होता है ना, तो उसके लिए आप एक तो से ये इमेजिनरी उसका डायमीटर है कि कंडक्शन के लिए उसकी कितनी लेंथ चाहिए उसे या कितना डिस्टेंस चाहिए. तो ये करेक्टरिस्टिक लेंथ उस डिस्टेंस को बताती है कि कंडक्शन कितनी लेंथ के क्रॉस हो रही है. ठीक है,
ओके सर.
ओके जी. Thank you for asking that, because it was quite intricate concept. So thank you for asking this concept. And now, because there is another concept of dimensionless time, which is called Fourier number. One thing we have already learned, that is Fourier law, that is for the conduction, but this is the dimensionless time. This is. So if we write that theta upon theta I formula which we derived in the beginning, so we can log of theta upon theta I is equal to, it was equal to minus HAS rho Vc into time, right? So if we take this bit which is on the right hand side and try to simplify it, we are taking this bit and writing it again here. We can write HAST on rho Vc. Again we have written. Now if you remember from your concept of characteristic length, this volume divided by surface area, that is basically a LC. So we can write it H into T divided by rho into, because this bit is 1 upon LC. So we write here LC into C, right? So now we kind of try to put here biot number. So for the biot number, we should have something like HLC upon K, right? So if we want to have LC upon K being multiplied like this, then we also need that to be divided here. Okay? Then it means that we are writing it K upon LC, and then the next bit is T upon rho C. Okay? So what I did here, that I have multiplied LC and divided K here to introduce biot number here, because this is the definition of biot number. But because I have multiplied LC here, then I need to divide it here as well, and then because I have divided here K, then I need to multiply K here, right? So mathematically it is correct. There is nothing wrong. It is just a manipulation of this stuff. So I can write biot number here, and then if I rearrange it a little bit, then there is as well here LC, okay? Because this LC should also come here. So it is biot number. Then if I rearrange it a little bit, then I can write it. I can write it K upon rho C. Okay. This is K, this is rho C, so I take this rho C here, and then I can write here T upon LC square. Okay, so I have taken LC here and taken rho C here. So mathematically again correct. Now from chapter number 1, we know that K upon rho C is alpha, which is thermal diffusivity, right? So now we can say that we have got biot number into alpha T into LC square. Okay, and then this quantity, sorry, this quantity alpha T upon LC square alpha T upon LC square, that is Fourier number. And this is also a dimensionless property. How do we know that? Because we know the unit of alpha, that is meter square per second, time is second, and then LC square, that would be unit of meter. So meter would be cancelled out with meter, second would be cancelled out with second. So this alpha T upon LC square is uh, basically we have got this as a dimensionless time, which is because why we are saying a time, because this alpha and LC square, these are the geometric parameters or thermal parameters, and this is the time which we are talking about. So this is the Fourier number. So now it means that we can write our uh, relation here, which we from where we started, that was log of theta upon theta I, that is equal to, if I put it here, that would be equal to minus biot number into Fourier number, right? So from here, if I want to write theta upon theta I, that would be equal to exponent minus biot number into Fourier, right? So now we have written it in terms of dimensionless numbers, because the left hand side is also dimensionless, so it means that the right hand side would also be dimensionless, because theta upon theta is the ratio of temperature differences. So it is dimensionless, so the right hand side should also have dimensionless property, dimensionless quantity. So I hope that whatever I have tried to explain it on the whiteboard, it is clear to you. So if there is any query, you can ask now. Otherwise, we can have 5 minutes break and then we can continue from there. G. Anyone? Any query? Whatever we have done about the lumped capacitance method. Either my teaching method is quite good, or maybe I don't know that what is the reason of because only Jayad participates or Shahid participates more often, but that's fine if you, as long as you are understanding that what is being taught to you, so that is fine with me. So I think there is no query at the moment, so we can have 5 minutes break and then we will meet maybe at uh, at 4 o'clock. Maybe.
4 o'clock, sir.
जी दोबारा बताइए कम अगेन
नहीं सर, मैं कहता था 4 o'clock आ जाएंगे दोबारा.
बिल्कुल जी ठीक है जी I take that so because I think we have studied non-stop for more than 1 hour so we deserve a break of 8 minutes so see you at 4. Thank you. Okay, ji, welcome back. Let me share the lecture slides with you. So we are going to. Okay, so can anyone confirm that you can see the lecture slides on your screen? Sharis,
Yes,
Yayad?
sir.
Okay.
Yes,
Yes,
sir.
So,
sir.
okay, ji, let me quickly recap that what we have discussed up till now, and then we can do some two numerical problems. So, first of all, we talk about the lumped capacitance method. So, we are talking about transient conduction now, and then the main assumption of lumped capacitance method is that the temperature of the solid is spatially uniform. That it means that whatever the temperature is at the boundary, the same temperature would be at the center. So there is no temperature gradient within the body. So it means that basically the thermal conduction resistance is zero, which can only happen when we have got thermal conductivity of that object is very high. So here in the last bullet point, it is written infinite thermal conductivity. So now we are talking about the cooling or rapid cooling of a forged object. Forging means that we are heating it in a furnace and then we are putting it in for the rapid cooling or quenching in the in a tub of water. So if we do that, we know that this would lose energy to this surrounding water. So it means that E dot in would be zero, and E dot gen would be equal to zero because that is not a radioactive material. So it means that minus E dot out would be equal to E dot st. So if we apply the put in the values minus HAST minus T infinity rho Vc dt by this small dt, which is capital T is temperature, small t is time. So now we introduce the temperature difference as a variable theta, which is T minus T infinity. Then we can write it in this form, and from here, by the method of separation of variables, if we do the integration bit from theta I, which is the initial temperature difference between that object and T infinity, and to some other time where the temperature difference would be less than the initial temperature difference. So if we do that, we can write it in terms of this function, which is here Hs upon rho Vc. That is the inverse of thermal time constant, which we have studied. That is a product of thermal resistance to the thermal capacitance, which is RT into CT. So from here, we have also discussed the significance of that temperature constant and the thermal time constant. And then if we want to calculate the total energy which is being transferred from convection during that process, we need to do the integral of that. And then we seen that it is equal to this. So we see into theta I 1 minus x1 minus c upon tau, which is the thermal time constant. And then we discussed about the validity of lumped capacitance method. In the process, we defined Biot number, which is the ratio of HL upon K, and Biot number should be quite less than 1 to be able to have this method applied to that particular situation. So Biot number, we when says that very it should be less than zero point 0.1, and then we discuss about the concept of characteristic length, which is basically for the random body, which is volume divided by surface area. And then we discuss about the concept of Fourier number, which was alpha t divided by LC square. So this is a dimensionless time. So we have discussed up till now. So if there is any query, you can ask. Otherwise, we can do numerical problems for this lumped capacitance method.
Sir, what does capacitance mean, thermal capacitance?
It is the ability of a material to store energy. So if you look here in this formula, rho into V, that is mass, into C, that is the specific heat. So if you remember from your thermo knowledge, what is this Cp or Cv? That is basically the amount of energy needed to raise the temperature of 1 kg by 1 degree centigrade. Is that right, Minahil?
Yes, sir.
So it means that if this quantity, the product of mass into C is large, so it means that if we want to vary its temperature, we need more heat transfer, right? Rho V into
Yes, sir.
C. So that is the concept of that thermal capacitance. So that is the ability of a material to store energy. So if a material which has got a greater ability to store energy, so in that case, changing its temperature would require more heat transfer as compared to a body, because if the mass is less, then if the heat transfer, then we require less heat transfer to change its temperature. But if the mass is more or this C value is more, then we need more heat transfer rate to change its temperature more rapidly. So that is the concept of capacitance, thermal capacitance, to be precise. Okay, ji, maybe it answers your query. Is that
Yes, sir.
right? Okay, ji, thank you. So now we move on to the numerical problems. So for, the first problem for this is that we have got some steel balls which are of 12 mm in diameter. They are annealed. Annealed is the process where we forge a material in a furnace, that we heat it to a higher temperature, and then we slowly cool it in an environment. So basically we put it in stationary air. So it means that it would cool down a little bit at a slower pace, gradual cooling process. So that is called annealing process. So first of all, we heated it up to 1150 Kelvin, and then we slowly cooled, which is basically the process for annealing, that is to 400 Kelvin in an air environment. So we are putting it in a stationary air environment, so that would have a less cooling rate, gradual cooling, for which T infinity is 325 Kelvin, and H value for that air is 20 watt per meter square Kelvin. Assuming the properties of the steel to be, steel की properties given है, K is equal to 40 watt per meter Kelvin, rho value is 7800, and then C value, which is the specific heat capacity, that is Cp or Cv, that would be equal to C in this case, that is 600 joule per kg Kelvin. Estimate the time required for this cooling process. So it means that once we put that in that air environment, how long it would take it to the temperature to decrease from 1150 to 400 Kelvin, right? So K value, you can see it is quite high, 40 watt per meter square Kelvin, but it is not infinite value, as it was the assumption of lumped capacitance. So it means that first of all we need to calculate Biot number and see that whether that value is less than 1. So if we remember the definition of Biot number, that formula, that was equal to HLC upon K. Now LC in this case would be characteristic length, which is equal to volume of a sphere divided by surface area of a sphere, right? So this is our schematic of that. Diameter is given, steel properties are given, air properties are also given. So first of all, we calculate the characteristic length, which is volume of a sphere divided by surface area of a sphere. We know that volume of a sphere is basically 4 by 3 pi r cube, या फिर we in terms of diameter we can write it pi d square, pi d cube by 6, and the surface area is 4 pi r square, or alternatively in terms of diameter, that is pi d square. So if we kind of simplify it, that is LC becomes equal to radius of the sphere divided by 3, right? So I hope that this simplification in terms of radius is understood. So now we put it in the Biot number formula, which is HLC upon K. H is given equal to be 20 watt, R outer, which is 0.012 meter, and then that is diameter. So the radius would be 0.006. So when we divide it by 3, that would be equal to 0.002 meters, and then divided by 40. So now if you see the ratio of this or Biot number that comes out for this particular problem, it comes out to be 0.001. So as this value is less than zero point 0.1, so it means that we can safely apply lumped questions method. It means that when we do the calculation, in the end, the results, whatever the time value would we get from this analysis, that would be very close to the real cooling time. So if this value comes out to be here biot number 1, then the time which we can equally apply the lumped question method. Even then no one can stop us. But in that case, the time which would come out from this calculation, that would be quite different from the actual cooling process. So that is that we mean to say that the error in the calculation by this analysis would be quite acceptable if the biot number is less than zero point 0.1. So in this case, because it is 0.001, so it is quite less than that, 10 times less. So basically, we are saying that the calculations would yield a very accurate actual time. So now the next thing is that we apply the formula as in the whiteboard. I circled some formulas, so it is one of them. T is equal to rho v Cp, not Cp may be equal to C divided by HAS into log of theta I upon theta. Now, what is theta I? Theta is the initial temperature difference, Ti minus T infinity. Ti is 1150, T infinity is 400 Kelvin. Now, I think 325 Kelvin, I think. Not 400, 325 Kelvin. And then what is the temperature, final temperature? That is 400 Kelvin here, and here, sorry for that, it should be T infinity, not infinity. So I would make this correction and send you the slides. So it should be here. Please make this correction at, don't be confused with this infinity. It should be T infinity here, not infinity, right? So that is a typo mistake. So I would correct it at my end. So please be clear about this. So the rest of the things, they are quite straightforward. Rho value is given, volume we can calculate, that is 4 by 3 pi r cube, or that is basically in terms of diameter. So if we put in the values, rho v, and then c value is given, h value is given, v upon as is equal to r outer upon 3. So if we put those values, so it is just the matter of putting the values. So if we calculate the time, that would come out to be in seconds. So it means that it would take 1122 seconds to cool this steel object from 1150 Kelvin to 400 Kelvin, which is basically, if we divide it by 60, we would get some the value in terms of minute. It would be around 18 minutes. So in hours, it would be 0.312, right? So I hope that this point is 18.36 minutes. The answer would be in hours. So it means that it is quite acceptable to anneal this, because it is taking quite less time. 18 minutes is quite manageable. Okay, ji. So this was the first problem. The second problem, that is a little bit more difficult. If we, I read the statement: a solid steel sphere whose thermal properties and rho value, C values are given, 300 mm in diameter. It is coated with a dielectric material layer of thickness 2 mm. Now we have got a material, solid steel sphere. We have insulated it with a dielectric material whose thickness is 2 mm, and then thermal conductivity of that dielectric material is 0.04 watt per meter Kelvin, right? The coated sphere is initially at a uniform temperature of 500 degrees centigrade, right? And then it is suddenly quenched into a large oil bath. Now we are talking about quenching, which is rapid cooling, and for that we usually use liquid, because for the liquid H value is quite high, so it results in rapid cooling. So for which T infinity is 100 degree and H value is 3300 watt per meter square Kelvin. Estimate the time required. So time required to reach from 500 degree to 140 degree centigrade for this sphere. So now we have got one additional resistance in addition to the convection resistance. So now because for the dielectric material we have got conduction resistance, which is L upon Ka. L value here is 2 mm, because that is the thickness of that dielectric material. K value is given, and then area we can calculate from the that here. Or we can talk about when we want to combine conduction resistance with convection resistance. Was there any parameter which we discussed in chapter number 3? Was there any parameter? If you remember, we talk about overall heat transfer coefficient, which was U is equal to 1 upon RA. If you remember from chapter number 3, overall heat transfer coefficient, which was represented by the symbol U. U was equal to 1 upon R resistance, total resistance into area. Okay? So we would make use of that, or this is the schematic we have got here. Sphere, if we see that there is a dielectric material there, so it means that now the heat which is going to be conducted away from this sphere, it would have two resistances. One is the conduction resistance of dielectric material, and then the second resistance is the convection resistance. So it means that we need to calculate the total effect of these two resistance. So for that we would calculate U value, which is the overall heat transfer coefficient. So first of all, we calculate the total resistance flux, that is equal to L upon K. So L upon here L is the thickness of this dielectric material, which is 0.002, and then K is the thermal conductivity of this material, which is equal to 0.04. Here you can see, and then because we are talking about resistance flux, so that's why we have taken area here, because we are talking about flux of resistance. So here we have got 1 upon H. So H value is given out to be 3300 watt per meter square Kelvin. So if you compare this value from the last problem, here it is 3300 watt per meter square Kelvin. Here, because it was air, so here the value of H is 20 watt. So you can easily see the difference between the H value for a gas and a liquid. ठीक है, लिक्विड के लिए देखें तो वो 1000 में है, जबकि एयर के लिए वो वैल्यू लेस देन 100 है. ठीक है, so quenching के लिए फिर we should use some liquid like oil or water. We can also use that. So from here we can calculate our flux, which is 0.0503, and then from here if we want to calculate U is equal to 1 upon R flux, that is R into area basically. So that is R flux. So if we calculate that value, this is 19.88. Now in Biot number definition, where we use LC upon K, then there would be ULC upon K, because now we have got H was the inverse of resistance there, but now we have got inverse of resistance equal to U. So for the Biot number and as well as for the calculation for the time where there was H, that would be replaced with U, because now we have got two resistances. One is for the dielectric material and one is for the surrounding air. So from here we can see Biot number is equal to ULC upon K, which is U into R naught upon 3 divided by K. That is equal to, now U value we have calculated R naught upon 3, because we know the uh, diameter of that steel ball is 300 mm, so the radius would be 0.15. So okay, they have written in terms of diameter, so diameter divided by 6, or it can be 0.15 divided by 3 divided by K value. Now this K value is for the steel, right? From uh, where the heat is being transferred by conduction. So that value is here. So we can see that 0.0204 value comes out. So this is less than zero point 0.1. So it means that assumption of lumped capacitance method would be good enough for this analysis. So then again we can use the same formula for the time here. So now you can see that there was a replacement of U with H. In the original derivation we had used H here, HAS, but now we have got UAS because we have got additional resistance of dielectric material. So it is just a matter of putting in the value. Rho value is given, C is also given, V upon AS is D upon 6, and T of 0 is 500 degrees centigrade, T infinity is 100. The temperature, the final temperature where we need to find the time for, that is 140 degree minus uh, this 100. So if we put in the values, now you can see that even by using the quenching process, the time required is 7 hours. And in the previous numerical, even we did the annealing process in air, that only requires 18 minutes. So why is this difference between these two values? Now, getting one value is one thing, but interpreting it in terms of physical, that why it is so much difference, because in the quenching process we were expecting a little bit more rapid cooling. So why it hasn't got this 7 hours? Any reason for that? By looking at the problem statement, anyone? Now that is some engineering uh, thinking, which is very essential for you guys. Why it requires 7 hours?
So because of dielectric medium,
Okay,
the
the
resistance will increase.
one thing is dielectric material. Excellent observation. Who was this?
Small sir.
You, Usman. Thank you very much for your contribution. One thing he has pointed out, that because there was a dielectric material, so because now the heat which would reach here at the boundary, it would experience additional resistance to go out because of that insulation. Because K value, if you look at this 0.04, that is for the insulator basically. Okay, so that value is very low. So that is one reason. Okay, anything else? Here the diameter is
सर के की वैल्यू
300
बहुत छोटी है.
के की वैल्यू बिल्कुल जैसे बिल्कुल ठीक बात की. उसके अलावा अगर आप साइज ऑफ दिस स्फीयर देखें, यहाँ पे है 300 mm. ठीक है, और अगर पिछले प्रॉब्लम में जाएं, उसकी वैल्यू देखें तो 12 mm है. अब 12 mm is a very small object, so it would naturally require a very less time to cool down. But here it has got maybe 30 times more diameter. ठीक है, तकरीबन अगर 30 टाइम्स नहीं तो 25 टाइम्स मोर डायमीटर. तो इसका मतलब ये कि नाउ द ऑब्जेक्ट विच रिक्वायर्स कूलिंग, इट वुड हैव हाई थर्मल कैपेसिटेंस. व्हाई इज दैट? because volume is very high. Rho Vc was thermal capacitance ना, जो कि हमने पढ़ा था lumped capacitance में. Rho Vc was equal to C, which was thermal capacitance. So now because the volume is very large as compared to the previous case, now it means that the thermal capacitance or thermal ability to store energy is quite high. So it means that in addition to that we have got additional convection resistance. So if we want to use air instead of oil here, then maybe it would take weeks to cool down. Okay, so it is our requirement to use that oil bath here to take that cooling times down to 7 hours. What if we have used air here? Then it would have taken maybe a week, maybe more than that. So that is not kind of feasible in terms of any facility where these uh, objects are being forged and then cooled down. So because that timing should be very less in terms of production, because efficiency depends upon the less time of production, so that more can be produced. So that's why they are using here oil bath. Okay, so that was something which I wanted to emphasize, apart from the numerical calculation, because that is also equally important. But in my view, that interpretation of those numerical values in terms of actual thing which is happening, that is even more important in terms of your engineering knowledge or engineering sense. So I hope that this would give you a better understanding of convection. So we have only discussed one topic from chapter number 5. Now that was chapter number 5 of Incotaya book. Now we would move on to the convection without any further delay, because convection is a little bit more complex and difficult as compared to conduction, because it requires the solution of